Okay, so the last thing we need to talk about is net force. Now, net force is fairly simple most of the time because it's exactly what it sounds like. The net force is really just the sum of all the forces. So if I say that I have F1 plus F2 plus F3 plus ... etc. So as many forces are acting on an object added together, I will get the net force. However, there is a second formula for net force as well, because it is a force and it still follows the F equals ma rule. So if you take the total mass and you multiply it by the net acceleration, so how much it's being accelerated in a single direction, you'll get the net force, okay? So that means if you see an object moving, accelerating, and you know its mass, you can come up with its net force, even though there might be various different forces acting on it. To give you an idea of how this works, let's just take a look at a simple problem here. I'm going to look at a box. I'm going to make it something easy. It's a 10 kilogram box, okay? So let's say I have an applied force of, let's say, 100 newtons, okay? And then let's see, I observe it accelerating in the same direction as the applied force, but only at 5, that's a 5 by the way, meters per second squared. Well, that's going to be my net acceleration, and my mass, my total mass is 10 kilograms. So I can figure out my net force acting on it. And so my net force acting on it, if I add these together, I have 10 kilograms, and I have 5 meters per second squared. But that's only going to give me 50 newtons. So my net force is only 50 newtons for this. But I can see I'm applying a 50 newton force to it. Well, that just means there's another force resisting that motion that's part of these up here of the forces that needed to be added together. And you could probably predict that there was something like friction. And if it's moving, it is a kinetic friction. And I can figure out the value of that based off the fact that my net force is 50 and my other force is 100. So if I have 50 minus 100, I'm going to get that this is equal to a negative 50 newtons. Okay? So you can calculate these things based on these two formulas to figure out a good deal about it. However, you notice that I was only looking at the x-axis. Well, that's because I could look at the y-axis as well, but I noticed that it's not moving in the y. So if it's not moving there, I know I have the force of gravity, and then I'm going to have a normal force that we talked about opposing that force of gravity, keeping it from going in the floor. My net force would still be equal because even though 10 times 9.8, a negative 9.8, is going to be negative 98 newtons, I know that that normal force just must be a positive 98 newtons, and so they canceled each other out in the y direction. Since it's canceled out in the y direction, I don't have to worry about it moving anywhere but in the x direction, and that's the only way that I have my acceleration. But that's also important why both acceleration and force are vectors. Okay? So technically I should have had these little vector arrows over all that up there. It's all vectors, and those directions make a big difference in it. Because they're vectors, let's take a moment to think about what would happen if you had that same 10 kilogram box, but now you only had two forces acting on it. So now it's like in the void of space, we'll say, but you have two applied forces. You have one applied force of, let's say, 10 newtons straight up. and then you had a second applied force that is also 10 newtons, but you had it straight to the right, okay? I'll call that 2 and that one 1, I guess. All right, so if those are the only two forces acting on it, you're still going to have a movement from this. Your movement is just not going to be straight up or straight to the side. It's going to be at an angle. In fact, if it was straight up and straight to the side and it was both equal amounts, it's probably going to be at a 45-degree angle from horizon in between the two that it would be moving. And this would be where your net force is going to be right there. But you can't just straight add 10 and 10 and get your net force being 20 there, because part of this force is pulling it to the side, part of it is pulling it straight up. And so those vector components would actually work together, and they're going to form a right triangle. So think about if I laid them like that, tip to tail like we did before, and this one's 10 newtons and this one's 10 newtons, you could see very easily that you can use a squared plus b squared equals c squared. So if I square both those sides, that's 100 plus 100 equals 200. The square root of 200 is roughly 14.1 newtons. And that's actually what our net force would be 14.1 newtons. And then I said in the 45, the way I did that is I just simply used our inverse of tangent rule. Remember that tangent of theta is equal to opposite over adjacent, right? And so I could say that theta, that angle, is equal to the tangent inverse of opposite over adjacent, or in this case, 10 divided by 10, which is 1. So the tangent inverse of 1 should equal 45 degrees. Now, this same combining of vectors can be used even if you have a lot of different angles of force acting on something. So let's say I had one that's like that, and let's do one that's straight down, and let's add some values, 10 newtons, 15 newtons, and let's make this one 35 newtons. Okay, and then I'm going to need some angles, okay? So a lot of times for these, you base this based off of a sphere, right? And so you would say this is your 0 marker, and that's usually the positive part of your x-axis. And so that you would measure things from like that one. That's just going to be something like let's say 45 for right now. 45 is a nice, easy angle. And then you're going to have this angle, which is, if you look, since it's straight down, that's just 180 plus 90. So that one's going to be equivalent to 270 degrees, 70 degrees, right? And then this last one, technically it would go all the way around. And so you could calculate that, and it's going to be something probably closer to like 310. But you'll find out what's a lot easier is once they get past a certain point, that 180 marker, let's just look at this one and say, well, that angle is 90 degrees, and this angle is 50 degrees, okay? And you can do your calculations based on that, and you would have to break each one of these into its vector components and then add those vector components. You remember the formula to do that, right? If you don't, I'll go ahead and help you out. So you have vector A, which is really just equal to A of x and A of y. You then have vector B, which is equal to b of x plus b of y, and even vector c, which is made of cx plus cy, and you can add all of those together and you'll get a resultant vector, okay? Or at least you'll get the resultant vector components. Remember, in all of this, you're adding straight down the x and straight down the y. So this is add x, add y, and this is add x, okay? And that will give you these two values right here. With those two values, you can figure out both the magnitude and angle of that resultant vector. So if you're thinking about this in terms of force, if all of these are forces, then it's going to give you your net force as your resultant, okay? That net force will be in a singular direction, even though all of these are made of different directions. We use something called a force wheel in order to do that. But to work that out, I might have to do a whole nother video just working out a problem because it takes a little bit of math and a little bit of time to get that done. I'll see if I can do that later.